Welcome back to College Algebra. Today we are solving equations with exponentiation and logarithms. Exponentiation might be a new word for you, but when you look at it, you'll see the word exponent, and really all we're talking about is using exponents or raising things to powers, but we're doing it in a special way. The word logarithm, many of you are probably familiar with. You've probably seen it before in high school math at some point. But if you're like most people, you could use some more work coming to grips with what a logarithm really is. And so the key to understanding logarithms is to think of them through the lens of exponents, and then they might make more sense. If you've been with us the last few lessons, you know we've been discussing inverse operations, where an inverse operation is just an operation that has an opposite effect on the equation of the one you started with. We've seen three main examples so far. We've seen that addition and subtraction are inverse operations. We've seen multiplication and division are inverse operations, and we've seen that powers and roots are inverse operations. So whenever you add or multiply or take a power, you can undo those operations by subtracting, dividing, or taking a root. So we have all these inverse operations and how they work, and today we're going to be introduced to two new inverse operations. The idea of exponentiation and the idea of a logarithm. Let's talk about it. Let's look at an example, because these words are kind of big and might be a little intimidating, but hopefully the example will help make more sense out of it. Our example is 2 to the x. So this is an equation that might be familiar to us. We just take 2 and we raise it to some power x. Well, the inverse of this is what we're going to call exponentiation, raising something to our x power. The inverse of this exponentiation is going to be log base 2 of x. And so what is a logarithm? Well, logarithms are kind of hard to understand in their own context, just like a square root is kind of hard to understand in its own context. But if you understand a square root as the opposite, or something that has the opposite effect of a square, then you can understand a logarithm as something that has the opposite effect of this exponentiation process. And hopefully that makes sense. And you see my second example here, 10 to the x log base 10. And so the base here that we're using for an exponent and the base here for the log, whenever they're the same number, then they're inverses of each other. They have inverse operations. I want to start by asking a question, which might be a pretty natural question to ask. What is the difference between this phrase that I used, exponentiation, and this other phrase, raising to a power? So what's the difference between taking something and raising it to a power and the idea of exponentiation? Well, the big difference is raising to a power might be something like an x squared equation. So notice for the x squared equation, you took whatever it was you're interested in, whatever number equation, whatever it was you're interested in, and you squared it. So you multiplied it by itself again. So you multiplied it by itself twice. So you took that number and you squared it. Exponentiation is similar but the opposite. So an exponentiation is 2 to the x. You took whatever it was you're interested in, whatever number equation, in this case it's just x, and you use 2 as the base and use that number as the power, as the exponent. So exponentiation, so when you want to raise something to a power, you add the power to the exponent. Exponentiation, when you want to use exponentiation, you take whatever it is you want to raise and you use it as the power itself. This might seem confusing, but hopefully we'll get very comfortable with it after a little bit. But let's start with just two basic examples. Our first example is, just to compare these two ideas, our first example is 2 to the x plus 3. If we take 2 to the x plus 3 and want to raise it to the second power, you get 2x plus 3, and you raise it to the second power just like this. And so you see, raising to a power, raising the second power just meant that the power comes right up here in this term. Exponentiation, on the other hand, if I want to use exponentiated by 2, then I take 2 and raise it to the 2x plus 3. So you'll see in one's case, right, in the first case, my 2x plus 3 stayed on the bottom, and my new part, which was my second power, went right up here into the power. Compared it to the second, where my exponentiation, what I started with originally, is now in the power, and my new part is down here in the base. So it's very similar to powers, except the role of the base and the new number that we've added to our problem have been changed. So this is called exponentiation. A word about exponentiation, this is not a common word. This is not a word that is used throughout a lot of math classes. But I find that in math we don't have a really good word for saying what this process is. So I've decided to adopt this one, and I'm going to use it. And I hope that it helps clarify the difference between saying raised to a power and exponentiated. So I'll try not to say raised to a power when I'm doing this operation. I'll try to only use the word exponentiation when I use this operation. Let's look at a couple examples and see if we can use this big idea to solve some problems. So problem number 1, we have 2 to the x equals 10. And so the question is, if you have 2 to the x equals 10, what are we going to do with it? So focus your attention just over here on the right. We have 2 to the x equals 10. The question is, what are we going to do with this problem? Well, let's go back to the very first conversation we had and realize that exponentiation and logarithms are inverses of each other. And notice what is going on in this problem. This 2 to the x is an exponentiation problem. So if we want to have the opposite effect, if we want to undo this 2 to the x power, what do we have to use? We have to use a logarithm. And so we do that by applying logarithms to both sides of the problem. So I'm going to put a log right here, and then I'm going to put a log right here. Let me just rewrite those so we can see them a little more clearly. You'll see that over here we have log base 2 of 2 to the x, and over here we have log base 2 of 10. So what we've done is we've applied our logarithm to both sides of the equation. We've taken a log of this side and taken a log of this side. Now the question is, what remains when we take a log of this side right over here? We'd have log base 2 of 2 to the x. We should get just x all by itself. Question is, why should we get just x all by itself? The answer is in this phrase that I described, and that's logarithms and exponents are inverses of each other. And so inverses means this raising it to a power, exponentiation, has one effect. The log has the opposite effect. It undoes what we just did. So this log and this 2 to the x, you could say the word cancel. I prefer the word undoes. They undo each other. And what's left on the other side is log base 2 of 10. Now, I am perfectly happy with you circling this as an answer for yourself. However, some of you may find this a little unsatisfying. If that's the case, you can put it in your calculator and come up with an answer. 3.321 is what I got. 219 is what I got when I typed it into my calculator. And these two things are the exact same, so you can choose the solution that you like. If you're struggling or having trouble putting this into your calculator, look for the link at the top of the page, and it'll send you to a discussion of how to do logarithms and exponents in your calculator. Perfect. Let's move on to our next problem. Our next problem is the log base 2 of x equals 1.5. In this situation, we want to think of it the exact same as we did before, except this time, what do we have attached to the x? We have a logarithm attached to the x. So how do we want to solve our problem? We want to solve our problem by using exponentiation. So how do you use exponentiation? Well, we use exponentiation with a base of 2. So we put 2 here and we raise the whole thing to the power of 2. That's what exponentiation is. It means that what we used to have is now in the power. And over here, what we used to have, 1.5, is now in the power of 2. Let me rewrite this so it looks a little bit nicer. You see that on one side we got log 2 to the log base 2 of x. And the other side we got 2 to the 1.5. Now why do we do this? We chose this process of exponentiation simply because it's the inverse operation of logarithms. And so the inverse of the logarithm, they undo each other. They have the opposite effect in the equation. And so all that's left is x. And over here, we get 2 to the 1.5. This, in my mind, is a pretty reasonable answer. However, you could type it in your calculator if you want and get 2.8284, etc. These decimals keep going as long as you'd like them to keep going. Many people find the idea of a logarithm here somewhat mysterious, but my goal is through this class and through the rest of the course, so understand that coming to really richly understand logarithms is not something that happens in one day. You experience them, you interact with them, and you work with them, and you slowly become more and more confident with them and more comfortable with them. Now let's look at a more complicated example. We're going to look at log base 10 of 4x plus 40 plus 8 over 5 is equal to 2. If you've been following along the last few lessons, what you know is the way we attack these things that are complicated, that have lots of different pieces, is by always moving from the outside in. And when I say outside, I mean the last thing to interact with the x. So as I look through here, I see that x is first multiplied by 4, then it's added by 40, then all of that is put inside the log equation, then we add 8 to it, and finally the last thing we do is divide by 5. So you have to kind of know your order of operations, you have to follow through and be able to read through the equation, but when I look through all this, I see that the last thing to happen to my equation was this 5. So that's going to be the first thing I'm going to undo. A 5 on the bottom means that the last thing we did was divide by 5, so I'm going to use the inverse of 5, and that's multiplication. So I'm going to multiply both sides by 5, and I'll get my new equation, which is log base 10 of 4x plus 40 plus 8 is equal to 5 times 2, which is 10. Now I look through this equation again, and I see that this whole part went into the log equation, and then after I operated on the log equation, I did the plus 8. So plus 8 was the last thing to happen, so I'm going to subtract 8 from both sides, and I will get log base 10 4x plus 40 is equal to 2. Now as I look through, I see we have this 4x plus 40 placed inside the log equation, so the next thing I have to do is I have to somehow undo this log base 10. And the way you undo a log, as we've been talking all along, is we use exponentiation. So that means I'm going to take 10 as my base, and I'm going to raise both sides with 10 as the base and both sides as the power. So I'm going to exponentiate using this number 10. What I get in this side is I get 10 log base 10 of 4x plus 40. What I get on this side is 10 raised to the second power. So notice, in both cases, my 10, which is my exponentiation, in both cases, the 10 went in the base, because that's what it means to use this exponentiation process, and what I originally had went up in the powers of both sides. Why do we do this? Well, the reason we do this, here I'm going to come over to this side so I can have more space. The reason we do this is because this 10 right here and this log 10 are inverse operations of each other. So they have the opposite effect in the equation. And so all that's left in that equation is 4x plus 40. And so on this left-hand side, this 10 as the base and this 10 as the log base 10 in the power have the opposite effect of each other, and we're just left with 4x plus 40. On the right side, it's a number that we can calculate. We know what 10 squared is. We've done this a number of times. It's 100. Now at this point, we're down to an equation that looks pretty similar. It's something we've done quite a bit, so I'll go quickly and subtract 40, and we get 4x is equal to 60. Finally, I'll divide by 4, and then we get x is equal to 15. So this problem started off looking very complicated, and I hope, if it looked complicated, that's fine. It looks complicated to many people, including people who've studied a lot of mathematics. But the important thing is not that we know the answer when we start the problem, but that we know a process to get to that answer. And this outside in, using inverses, is a process that will get us there. The process involves first multiplying, then subtracting, then using exponentiation, then subtracting again, and then dividing. Taking off these pieces, 1, 2, 3, 4, 5 of them, one at a time, until we're left with x all by itself. Okay, let's look at this problem where we have 3 to the 0.4 square root of x minus 1.44 is equal to 12. As we look at this problem, we have to evaluate what was the most outside part so that we can undo that part first. And we notice that we have the x is first being square rooted, then it's being multiplied by 0.4, and then subtracted by 1.44, but all of this is within the exponent of the 3 to that power. So as I look through this, I see that the very first thing I need to get rid of is this 3, because that's the thing that's on the outside. Everything is inside of that exponent. And as you recall, the way we're undoing these is we're using logarithms to undo an exponentiation. So to undo this, I need to take log base 3 of all of this in order to undo that 3. However, of course, I can't just do to one side, I have to do to both sides. Let me rewrite so that we can read it more neatly. So we take log base 3 of 3 to the 0.4 square root of x minus 1.44 equals log base 3 of 12. Now as I look on the left side over here, the reason why I introduced the log is because log base 3 of 3 to a power, exponentiation and logarithms are inverse operations. So this exponent and this log should undo each other, and we should be left with just 0.4 square root of x minus 1.44 is equal to log base 3 of 12. It's perfectly fine and valid to just leave this as log base 3 of 12. I'm going to go ahead and type it in my calculator and get 2.26, realizing that this number actually continues much longer. Now as I look at this equation, I have to decide what is the next piece to be taken off. And as I look at this, I see we have 0.4 square root of x minus 1.44. This minus 1.44 is the outermost part. It's the last thing to interact with the x. So I'm going to add 1.44 to both sides. That's going to give me 0.4 square root of x is equal to, I have to add 2.26 and 1.44, and that's going to be 3.7 or 3.70, which I'll just leave right there. Now what I'm going to do is take this result and I'm going to rewrite it so that I have a little bit more space to work with. All I have to do now is get rid of this 0.4. We'll do the opposite of multiplying by 0.4, and that's to divide by 0.4. That gives us square root of x, and then we have 3.4 divided by, 3.7, sorry, I've got the wrong number here. 3.7 divided by 0.4 is 9.25. And then at last, the last thing I need to do is undo the square root, and when I do this, I can't forget everything else we've done so far. So in the last session we learned that square roots are inverses of powers, and so I need to raise this to a power, and I'll raise it to the second power because that will undo the square root. And that'll give me x, because the square root of x squared is x, and then I need to square 9.25 and get my final result, which is 85.56. It also goes 2.5, but I'm trying to just use 2 decimals here, so I'll just stick with 2 decimals and be pretty happy with this as my result. Now before we conclude today's lesson, I want to talk just a little bit about logarithms and the log base 3 of x just in general. In particular, I want to make a few points that are going to become important later in this semester as we start trying to manipulate and do some cancellation within expressions. In order to talk about logarithm, I want to talk about square roots to begin with. And I want to notice some things that we advise. So square root of 5, we think of this as just a number, and you could type in your calculator and get a number out for it. And you can kind of think about what number it might be. It's a little bit bigger than 2 because the square root of 4 is 2. So the square root of 5 is a little bit bigger than that. that makes sense to us and is a reasonable thing to write down. Similarly, we can write log base 3 of 5. Now this is less intuitive to us. It seems a little bit less obvious. But it itself is also just a number. It's a number our calculator can express for us. It's a number that comes from solving the equation 3 to the x equals 5. And so this is just a number itself that comes out for an answer. Similarly, we can talk about things like square root of x, which we're pretty familiar with. This is an x that's been operated on by a square root, where x is just some unknown number. You can replace any number you want for x, and this makes sense. This is kind of a reasonable expression to talk about. Similarly, when we do log base 3 of x, this is just kind of a reasonable expression. It's a number, x is a number, and whatever number it is, we operated with it using this log base 3 operation. We could do this with a calculator, we could do this by solving equations, but whatever the operation is, log base 3 acted on the number of x. I want to talk finally about what does it mean to write log 3 by itself. Well, the big point that I want to make, and that is often missed by students, is that log base 3 has a meaning only as an operation. This is not a number. This is not something that you should write down by itself. This has just as much meaning as writing down a square root with nothing inside of it. This looks really awkward, I bet. And you stop and think about it and you go, well, this is silly. Nobody would write a square root without something inside of it. We have to square root the 5 or the x. I want to say that once you understand logarithms, this is going to look just as silly as this. And that is that you would never write a log without saying what you were taking a log of. You wouldn't write log base 3. It would be log base 3 of 5, log base 3 of x. And so for a logarithm to make sense, you need to have something inside of it, something it's acting on. I say this because, importantly, we're going to do some things later this semester. We're going to do things like this and ask, can this be simplified? Now there's a real temptation here to try to simplify this problem as follows. To try to say we have an x squared on top and we have an x squared on bottom, and so these two x squareds should be able to cancel each other, leaving log 3 as my answer. Now there's going to be many reasons why this is not an appropriate thing to write down, but chief among them is the fact that log 3 is not something that's reasonable for an answer. Log 3 itself would be just as bad as writing square root with nothing inside and circling that as your answer. Similarly, we know that cancellation only works with multiplication, and so this is not log 3 times x. This is not a multiplication problem. This is a problem where x squared has been put inside the log 3 equation. So when I see something like this, I'm going to put a big don't do sign around it, and I'm going to couple that with a little sad face, because we don't want to do this, and it makes me sad when I see you do that. Similarly, you might try to look at some equation like this, where we have log base 3 of x plus 1 over log base 3 of x minus 1. And you might be tempted to look at these log 3's and say, oh, maybe these log 3's should cancel, and put lines through them and say maybe my answer should be x plus 1 over x minus 1. But when you do that, what you're really doing is you're treating log base 3 as a number, and you're canceling that number. But log base 3 isn't a number. You can't write it all by itself as a number. So similarly, this is also going to get a do not do sign. Do not cancel logarithms, only cancel numbers. And it's also going to get a sad face because it makes me sad when you try to cancel logarithms. So these are just a few notes for things that we're going to do coming up in the future that I want you to avoid, and I don't want you to make those mistakes when they come up. Let's end today as we end most every day, and that is I'll give you a couple problems that I want you to work on. I want you to go try them out independently, pause your device, and take just a minute to attempt them both and see if you can get the correct answer. Okay, we're back. You've unpaused your device. Hopefully you've given this a really valid attempt and found somewhat correct answers. The answers that I got are x equals 6.292 and x equals 1.524. And if you look on the right side over here, you'll see solutions to these two problems. So So click on these two solutions. If you had trouble solving the problems, then you'll be able to see me work through them. Thank you very much, and I'll look forward to seeing you next time.